Good morning, everyone. My name is Junwei Jing. I'm presenting our work, RHO, Robust Holistic OSM-Based Metric Cross-View Geo-Localization. OSM-Based Metric Cross-View Geo-Localization takes two inputs, a ground image and an OSM tile centered around a noisy GPS prior. The goal is to estimate a 3D camera pose, that is, the precise position U, V and heading angle theta. Existing methods leave three important gaps unaddressed. First, a robustness gap. Current models are trained and tested under clean conditions, but in the real world we encounter rain, snow, fog, motion blur, and exposure shifts. Performance drops by over 20% under such corruptions. Second, pinhole images only capture about 90-degree FOV. Panoramic images, with their full 360-degree coverage, are inherently more informative. Third, satellite imagery, the traditional reference map, is storage-heavy and often stale. OSM is 15 times smaller per square kilometer, community-updated, and better aligned with current ground views. To address these gaps, we make four contributions. First, we introduce CVPR, the first large-scale benchmark for robust OSM-based metric cross-view geolocalization, with 2.7 million images across 8 conditions. Second, we propose the RHO model, a two-branch pin-pan architecture. Third, the SUM module, which handles equirectangular distortion. And fourth, the POF module for fusing position and orientation. CVPR dataset contains 2.7 million 120-degree pinhole crops, 912,000 panoramas paired with OSM tiles, spanning 6 cities. We generate 8 variations: clean, rain, snow, fog, night, overexposure, underexposure, and motion blur, using Flux.1 context for weather and OpenCV for sensor noise. As shown in the comparison table, CVPR is the only dataset that covers 5 axes: pinhole, panorama, OSM, weather noise, and sensor noise. The key insight behind RHO is grounded in information theory. A panoramic image captures all surrounding landmarks regardless of camera heading, so its Shannon entropy is rotation invariant, ideal for estimating position. A pinhole image, by contrast, sees different content at different headings, so its entropy varies with orientation, making it ideal for estimating heading. This motivates our two-branch pin-pan design. Here is the overall architecture of RHO. The panoramic branch takes the 360-degree panorama, passes it through the SUM module to produce a clean 360-degree BV, and matches it against the neural map for a position score volume. The pinhole branch processes the 120-degree crop into a BV and produces an orientation score volume. Both score volumes are then fused by the POF module to output the final 3D pose. The SUM module addresses equirectangular distortion. It first splits the panorama into 3 120-degree pinhole views, then undistorts each one and projects it into a triangular BV. Finally, it rotates and merges the 3 triangles into a single equilateral triangle. The POF module performs 2-stage mutual refinement. It uses the panoramic position prior to guide the pinhole orientation estimation, and vice versa, allowing position and orientation to refine each other iteratively. On the clean CVPR benchmark, RHO outperforms OrienterNet on every single metric, achieving up to 8.72% improvement on orientation recall at 3 degrees, and 7.39% on position recall at 3 meters. More importantly, under noisy conditions, with both models trained only on clean data, RHO degrades far less. Compared to OrienterNet, our zero-shot degradation is up to 7% smaller on orientation recall, demonstrating significantly better inherent robustness. RHO also generalizes well. On an unseen city, we achieve an 11.9% average recall gain. And in our Sim2 real experiments on real-world weather photos, RHO reaches 81.8% orientation recall at 5 degrees under Rio rain, substantially outperforming the baseline. To summarize, we present CVPR, the first robust benchmark, and RHO, a two-branch architecture with SUM and POF modules, achieving up to 20%. Thank you for your attention.